Dear students, in this video we are going to discuss about how to perform deformation and stress analysis on a cantilever bar using ANSYS APDL software. Okay, so this is the problem given. A cantilever bar of length 800 mm, cross-sectional area 1000 mm square is considered for the analysis, which is loaded with 1000 Newton magnitude at its free end. Suitably, the material of the cantilever bar can be assumed to be steel. Okay, so the Young's modulus of the steel material can be taken as 2 into 10 power 5 Newton per mm square. So now we will discuss the step-by-step procedure to solve the given problem using ANSYS APDL software. So this is the ANSYS APDL page. So to solve the problem, first we have to define the problem in ANSYS APDL page. For that we have to go to the preferences first. Here we have to select structural problem, as a given problem is a structural type of problem. Then under preprocessor we have to define the element type. So here we can add, edit or delete the element types. First we have to add the element. As the given problem is a cantilever bar, so we can select the type of element as link element. Then go to material properties, material models. So here structural problem. Since the given bar is axially loaded, the response of the bar is also in the linear direction. Okay. Elastic, as the considered material of the bar element as steel, it is an isotropic material. The properties of steel material is uniform in all the direction, so we can select isotropic. So Young's modulus of steel material 2E5, 2 into 10 power 5 Newton per mm square. So Poisson's ratio value is not a matter here because it will not influence the deformation and stress. So then sections. So as the considered bar element is made up with uniform cross-sectional area, link, we can create only one section ID. So the area of the entire bar element is 1000 mm square. So now we can model the cantilever bar mentioned in the considered problem. Okay. So we can create the entire bar element with the aid of nodes and elements. So for following finite element analysis to solve structural problems, we have to subdivide the entire structure into convenient number of elements. At least we have to divide the entire element into at least 2 elements for performing finite element analysis. For that I have subdivided the entire cantilever bar into 2 elements. So exactly I have splitted the entire element into half equal elements. So this is element 1 and this is element 2, and the nodes are, this is the first nodal point, the intersection of the elements 1 and 2. So this is nodal number 2 and this is nodal number 3. Okay, so we have marked 3 nodal points to generate the entire cantilever bar element of 2 equal length elements. Okay, so we have to define these nodal points in the ANSYS APDL page with the aid of exact Cartesian coordinates positions. So the nodal position 1 can be taken as the reference. So the nodal coordinate position in Cartesian coordinates for the first point is assumed to be 0 0 0 origin. Okay. Since the cantilever bar, considered bar is distributed in the negative y direction, the nodal coordinate position for the second node is 0, minus 400, 0, and the nodal position for the third node point is 0, minus 800, 0. Okay. So now we can model the cantilever bar using nodes and elements. So nodes in active coordinate system, first nodal point 0 0 0 coordinate position for the first nodal point, apply. So now the second nodal point 0, minus 400, 0, apply. So now the third nodal point 0, minus 800, 0. Okay. So now we can join these nodal points to create the elements. So here there will be an option element and attributes. If the considered structural member is made up with more than one material, more than one kind of material, or it will be having more than one dimensions, that is cross sectional area, then we have to go to here to select the material number as well as section number to create the elements. So in the problem ellame same, that is the entire structure is made up of steel material as well as it is made up with uniform cross section. So now we can directly go to auto numbered through nodes. So click the first and second nodal points and apply. Okay, then click the second and third nodal points. Okay, so with the aid of the generated nodal points, now we have generated the elements. Okay, so then we can apply the boundary conditions. So for that, go to solution, define loads, apply structural displacement. So where the displacement is arrested and in either directions, in which are all the directions have been arrested அப்படிங்கறத இந்த பாயிண்ட்ல we have to represent. So on nodes, first nodal point is fixed in the problem, so select the first nodal point. Okay, in all the degrees of freedom the deformation is arrested, yeah? So all DOF. Okay, then we have to define the loading condition. For that, force or moment on nodes, load is applied in the third nodal point. Okay, load is applied in the negative y direction, so Fy minus 1000 Newton. So now we have completely defined the problem. So now we can solve the problem to get the deformation and stress results. Current load setup. Okay, so the solution is done. So to read the results, go to general post processor, plot results, contour plot, nodal solution, DOF solution, displacement vector sum. Okay, so now we can see the deformation result. The maximum deformation has been experienced at the free end with a value of 0.004 millimeter. So we can note the deformation experienced by the bar. By each section of the bar can be observed from the deformation plot. Okay, so if we want to directly read the results at the nodal points, then we have to go to list results, nodal solution, DOF solution, displacement vector sum. So along y direction, first, second and third nodal points have experienced the deformation of 0, minus 0.002 millimeter and minus 0.004 millimeter deformation respectively. Okay. Then to read these stress induced results, we have to go to the option element table. Okay. Define table, add. So to read the axial stress induced in the bar, we have to give the sequence number for axial load, that is LS1. Close. Then go to plot results, line element results, LS1. Okay. So this is the stress plot. So the entire structure has experienced uniform stress of magnitude 1 Newton per mm square. Okay. So this is all about the problem. Thank you.